Hello there. This video is on section 10.4, where we're going to be doing calculus using polar equations. In the previous section, 10.3, in the video, I introduced what polar equations were, how to convert between polar equations and Cartesian equations, and a little bit of calculus, like how to find the derivative, dy dx, in polar equations. So now in section 10.4, we're going to be doing some other calculus applications. For example, we're going to be able to find the area and arc length and things like that. So I'm going to give some examples and we'll be able to get going that way. Okay, so the first thing is that from geometry, if you remember all the way back in geometry, we had the area of a section of a circle. The area of a complete circle, you might remember as pi r squared, right? But if we take just a portion of that circle, it will be a portion of pi r squared. So suppose we mark out like an angle of theta, right? So we're looking for this portion of the circle. So we need to figure out what fraction of the entire circle that is. The fraction is theta out of 2 pi, because 2 pi is the entire rotation. So theta out of 2 pi would be the portion of the circle that is swept out through theta radians. So it's pi r squared times that fraction, times that portion. In other words, we have the formula that the area of a segment of a circle is just pi r squared times theta. How did I get that? Well, you have 1/2. I said it wrong. The area of a section of a circle is 1/2 r squared times theta. How did we get that? Because in this formula here, the pi and the pi divide out to give me 1, and I'm left with just r squared times theta and divided by 2. And the way that they write it, for some other reason, is not as a fraction, but the 1/2 in front. So 1/2 r squared times theta, which is the same, of course, as r squared theta over 2. So that's the area of a segment of a circle. In polar equations, what we're doing here is we're not finding the area. Well, generally, we're not trying to find the area between a function and the x-axis or y-axis. We're trying to find the radial area, which means if we had some crazy equation here, they gave us a graph, we would be looking at the area from the origin, the radial area, this area right in here, right? So not the radius to the x-axis, not the radius to the y-axis, but the radius, or the areas to the center, to the origin. Okay, so we're going to be doing our old calculus technique, which is doing slicing. So we're going to take the little slices here, and each little slice, we're going to find out the area, add up all the slices, and that is the standard way of figuring out the total area. So for a little slice, we got 1/2 r squared times d theta, because you have a very small change in theta. So our little slice area has 1/2 r squared times d theta as opposed to 1/2 r squared times theta. We get a little d theta, a little change in theta. And so if you add up all those little slices, you get this formula right here. This is a formula that you'll be using in this section. That is the radial area for a polar graph from some starting theta value to some ending theta value. Another formula to have written down, or if you would like to memorize those things, we did do parametric equations in 10.2, 10.1, 10.2, and we developed this formula for the arc length of a curve in terms of parametric equations. And that was just simply taking our normal dx squared plus dy squared equals ds squared. And just, that's the Pythagorean theorem, and just manipulating it using some algebra. So if you do another bit of algebra with r's and thetas, remembering that r is equal to, remembering that x is equal to r cosine theta and y is equal to r sine theta. If you just divide by d theta squared instead of dt squared, and you use these simplification formulas, you end up with this arc length of a polar curve, right? So I don't want to go through all the algebra. It's a little bit messy. It's a great thing to try practice because it's really cool how everything kind of cancels out. You get this really nice formula. It uses the exact same equations we've been using in the previous section, x equals r cosine theta, y equals r sine theta, and you just divide this whole thing by d theta squared and simplify. Okay, again, if you want to see me do it, just let me know and maybe meet them Zoom hours and I'll go through the steps with you. It's cool to try yourself if you want to do that. If you're curious, it works out quite nicely. It's this. I'm just going to leave it that formula there, and on request show you the reason why that's actually the correct formula. Okay, so let's do some example problems so we can see what's going on. This is not a terribly long section, so I'm going to do maybe a few examples of how this works, and then let you, go to town on the homework and ask questions if things arise. Okay, so my first example here is to find the area in the first quadrant of this polar function, this polar graph. So first of all, let's get a picture of it, see what's going on. This is r is equal to 4 sine 2 theta. So I've actually typed these equations in already. So 4 sine 2 theta is right here. And it's kind of like, I don't know, 4-leaf clover, butterfly thing. So that's 4 sine 2 theta going from negative pi to pi. And it asks for just one leaf, not 4 leaves. And we couldn't just find the area that's divided by 4 because honestly, we don't know if this is like repeating itself. Like maybe if I go from negative pi over 2, well, I do lose a leaf there. So you just have to be careful not just to assume that the thing is exactly the way you think it is. We need to do a little bit of math to like justify what we're doing. So for r equals 4 sine theta, what we're looking for is we're looking for one petal. So this is where we start at the origin where r is 0 and we go around, for example, this one and back to r equals 0. So it's going to start at r equals 0 and end at r equals 0. That's going to give us leaf. It doesn't matter which one we get. We just have to be able to start at 0 and go all the way over here and end at 0. So we'll be using just some mathematics to figure out when that occurs. This is the equation, and I need to find out when r is 0. There's the equation. I need to find out when r is 0. So let me go ahead and start doing that. I divide by 4, doesn't do much. Take the inverse sign of both sides. Divide by 2. Oops. Divide by 2. And that is my answer for theta. That's the angle. So I had to find the sine inverse of 0. Remember, unit circle. This is when the y value is 0. So where is the y value 0? That happens. So sine inverse of 0 says, what is the angle where the y value is 0? That's going to happen 0, pi, 2 pi, negative pi, etc. Right? There's lots of answers for these guys. But I have to divide by 2. So I'm going to get 0 divided by 2, pi divided by 2, 3 pi over 2, negative pi over 2, etc. So I get a bunch of different values for that. I just have to find 2 of them. Let me try the first couple, 0 and pi over 2. So let me go 0. Let me change you. There you go. 0, 0, and pi over 2. Yep, there we go. So that's one leaf of this, whatever, 4-leaf clover. So I know my theta values go from 0 to pi over 2. That gives me one of these leaves. All right, so now I'm going to be able to calculate my area. If you remember the formula for area, I'll go up here and remind you. Formula for area is the integral from theta 1 to theta 2 of 1/2 r squared d theta. So 1/2 r squared d theta integrated from theta 1 to theta 2. All right, so what is r? Well, we know what r is. R is this guy. What is theta 1 and theta 2? Well, we know what those are. Those are the ones we just found out. So the area is equal to the integral from 0 to pi over 2 of 1/2 times r squared. So that's 4 sine squared 2 theta Oops. It's 4 sine 2 theta all squared. I put the square in the wrong place, right? So let me see if I can fix that. 4 sine 2 theta squared, 1/2 r squared d theta. Okay, so assuming that I got that straight, and I can maybe simplify this a little bit, I get 1/2. 4 times 4 is 16 sine squared 2 theta d theta. 1/2 times 16 is just 8. So I can bring the 8 on the outside. And just to integrate sine squared of 2 theta, you're going to have to use the trig formula to simplify this. The fact that sine squared theta is 1 minus cosine 2 theta over 2 is the way you do that. I'm not too interested in you practicing all of your antiderivative formulas and methods. I'm more interested to see if you can do calculus on polar equations. So I'm okay with you going to technology to do this. So I would just go to something like Wolfram Alpha and try that. So I will go in here, area from, cannot type, from theta equals 0 to theta equals pi over 2 of 1/2. Oh no, I multiplied it out. So 1/2 times 16 was 8. And then I have sine theta squared d theta. All right, let's see if it understands that. It'll try to interpret it so you can know if it made a mistake in understanding what you wanted. It does not understand what I wanted. So let me make sure that I'm actually typing in correctly. I want 8 from 0 to pi, by the way. No, it is 0 to pi over 2. I just typed it in. I wrote it in wrong over here. So 0 to pi over 2. If you're wondering why is he putting pi there, the answer is because he was wrong. So 0 to pi over 2, sine squared of 2 theta d theta. So I think I forgot that. Sine squared 2 times theta. And let me get rid of the d theta thing. Maybe it got confused because that's weird. Area from theta equals 0 to theta equals pi over 2 of 8 sine 2 theta squared. Let's see if it understands that. All right. 8 sine squared 2 theta from 0 to theta over 2. Oh, this is not a surface area. So I'm going to have to pause the video and try to wrangle Wolfram Alpha to do this without wasting too much of your time with getting this to work. You got to try a couple times. I will try once more. Okay, I think I got it. So we have this integral 8 times the integral from 0 to pi over 2 of sine squared 2 theta d theta. So what I did is I used the extended keyboard in Wolfram Alpha so I could do the theta. So I have integral of 8 times sine 2 theta squared d theta from theta equals 0 to theta equals pi over 2. And it actually did it for me, and it gave me the answer of 2 pi, or 6.28 approximately. So we have this area is equal to 2 pi. That should be equal sign. All right. Well, my point here was to show you an example of how we found the polar area for part of this for this function here for part of it, which was sort of the first quadrant of it. And we had to use some algebra, some precalculus, to figure out what the limits were. And we got 0 to pi over 2, which matched up with this first quadrant petal of the four-leaf clover. Okay, on to the next example. Just on the next page. Example B, find the area of the region that is both inside this guy and outside that guy. Okay, so we're finding the area between two things, but once again, we're finding the radial area, the polar area between two polar functions. Okay, let's make sure we can do this. So I have typed these equations into Desmos so we can see what they look like. They are this guy right here, 2 plus sine and 1 plus cosine. So we're supposed to do inside the first curve, inside this red one here, if you're color-sighted, and outside the blue one, which is the smaller one here. The red one, the outside one, has got a little flat thing right here. It's not a circle. It looks kind of like a circle-ish, but then it gets really flat here. The blue one inside is sort of like a little heart thing on its side. Definitely interesting little equations. And we're trying to find outside the blue and inside the red. So I gotta find some limits of where to go from where to where. So it looks like they start right on here, and it goes all the way around to here. So this is the area like between the inside the red and outside the blue, right? Over here, it's the wrong. It's the blue is on the outside, the red is on the inside. So we don't want that. We want this stuff over here, starting right here, right around 2 for the x value, and ending over here when x is 0, although we can't really use x values because we're doing polar. So we got to find the angles, the angle there that corresponds to this sort of intercept. This is the x-intercept, and this is the y-intercept. So we need to figure out where the x and y-intercepts are for the red and blue graph, and then we'll know our limits, theta 1 and theta 2, of how to divide this up. We're going to, doing little rectangle things and finding the area of the outside minus the area of the inside, just like we do normally. But we got to find out where to start and stop. All right. So we do know that it's going to happen at x-intercepts and y-intercepts. X-intercept is when y equals 0. Y-intercept is when x equals 0. Basic math definitions. We are given, for example, the outside one is r equals 2 sine theta. So let's go ahead and do, oh no, it's not 2 sine theta, it's 2 plus sine theta. Excuse me, 2 plus sine theta. So let's go ahead and see what happens if we try to find out when either x is 0 or y is 0, we're trying to find the two intercepts. All right, so that's my equation. I do know, as always, that x equals r cosine and y equals r sine. Those are my basic definitions that we use again and again. So let's start with x equals r cosine. We know r, that goes in there. And we know x is 0. We know x is 0 because we're looking for the intercept, right? So we get 0 is equal to r, which is 2 plus sine theta. That's r, and then cosine theta. All right, so that's my equation for when I know x is 0, and of course x is r cosine theta, with the r given to us as 2 plus sine theta. Okay, so how do we solve this thing? Well, this is a product of two things. It's 2 plus sine theta times cosine theta is equal to 0. So with our basic idea of solving for algebra, when you multiply things, it equals 0. One of them has to be 0. So here we have sine theta is -2, which is impossible. The biggest sign can get is +1. The smallest sign can get is -1. It's not, you can do inverse sine of -2 on your calculator. It'll say undefined. This one, we want cosine to be 0. We want to find the theta value where the cosine or the x value is 0. So if you think about your unit circle, where is the x value 0? That's at pi over 2 or 3 pi over 2, or you can go backwards, negative pi over 2 or negative 3 pi over 2, etc. There's lots of them, as always, right? So you have lots of choices for what theta is going to be when we have x is 0. All right, so let's take the same equation and plug in y is 0. So we get y is equal to r sine theta. We're going to plug in the fact that y is 0. And of course, we know what r is. It's already 2 plus sine theta. And over here, so that's sine theta. Over here, again, we have like two things multiplied to be 0. So either 2 plus sine theta is equal to 0, which we know is not possible. So not possible. I guess I'll just do undefined. And the other one has sine theta 0. So now we need the y value to be 0. The y value is 0 when theta is equal to 0 or pi or 2 pi or negative pi, et cetera, et cetera, et cetera. So we got a bunch of those values. Okay, so we have a bunch of candidates for one intercept and a bunch of candidates for the other intercept. So pi over 2 is the first one here, 3 pi over 2 is the second one, negative pi over 2. Let's try some out. 0, pi, 2 pi, things like that. Okay, so we need to have one of these over here on the left in blue and one of these over here on the right in red. Let's just try 0 to pi over 2, see if that works. So we want this top guy, 0 to pi over 2. Oh, I didn't go far enough. So it looks like 0 nailed right here, or one of them nailed right there. Let's try the next one, which is 3 pi over 2. Oh, there we go. So for our possibilities, we had 0, pi, 2 pi is one of them. And we had pi over 2, 3 pi over 2, negative pi over 2. So pi over 2 got only to the top part. It didn't go all the way around. When I chose 3 pi over 2, it went all the way. So it gives that portion right there, the red. I got to do the same thing for the blue, right? So for this other equation here, 1 plus cosine theta, I do the exact same calculations and find out exactly what I need there. So for this guy, can I move you over? For this guy over here, I'm just going to take the other equation, which is over here. R equals 1 plus cosine theta. And I'm going to find out the intercepts for that. So R equals 1 plus cosine theta. And I'm going to find out when x is 0 and when y is 0, because that's where the two graphs intersect on our graph. I know x is r cosine theta. And I know r is 1 plus cosine theta, because that was given to me. So I get r times cosine theta, which is 1 plus cosine theta times cosine theta. And I want x to be 0. So 0 is right here. So 0 is equal to r cosine theta, or 1 plus cosine theta times cosine theta. I have two things multiplied together. So either 1 plus cosine theta is equal to 0, or I have cosine theta is equal to 0. So over here, I have cosine theta is -1, and that happens, whoops, equals -1. And that happens, I got to write this better, because people are going to look back at this and say, what is he saying there? What is he writing there? Okay, so this is cosine theta equals -1. So I want the x value to be -1. That happens at pi and at 3 pi and at negative pi, etc. And over here, I have cosine theta is equals 0. I want the x value to be 0. So where's the x value 0? That's pi over 2, 3 pi over 2, negative pi over 2, etc. So I get lots of possibilities for theta. I get these values for theta, I get these values for theta, and then of course I get the symmetrical ones, right? So I got a ton of values for theta when just x is 0. I haven't done y equals 0 yet. So I got to plug in y equals 0, see what's going on, and do the same sort of calculations. So I need more space. So once again, I'm going to take my equation. What am I doing over here? Let me go back up here. Okay, so I'm going to take my equation. I'll do it in blue this time. Y equals r sine theta. I know y has to be 0. I know r has to be 1 plus cosine theta. And I know r is being multiplied by sine theta. And since they're equal to 0, very nicely, I can just solve them. This is sine theta 0. You'll notice that we get the exact same equation we got before. So we already know that those solutions are pi and 3 pi, etc. So we already solved that one in the other situation over there to the left. So this one over here is sine theta 0. So when does sine theta equal 0? Well, that's when the y value is 0. So that's going to be 0 or pi or 2 pi or negative pi, etc. So we get a bunch of values for theta. Again, we're going to have to try some. You're going to notice a lot of similarity between these and the last ones we found. So you could just try some out. I'm going to try the same ones we tried out before, 0 and 3 pi over 2, or maybe I'll try 0 and pi over 2 just to see what happens. So 0 and pi over 2. No, that didn't do the whole thing. Let me do the 3 pi over 2. There we go. Okay, so all that work was just to find the two theta values where we start and stop, the red one on the outside and the blue one on the inside. So we know we're going to be splitting this up into lots of little radial, areas, and we're going to be taking the outside one, the outside radius, and the inside radius, subtracting the two areas, and the theta values go from 0 to 3 pi over 2. All right, so that really was the hard part. So what is the rest of this now? Do I have space? I'll have space. I don't have space because this one's over here, but I'll just make space over here. So area, you remember the area is 1/2 r squared d theta. And I have to subtract off the outer area minus the inner area. So it's going to be sort of the inner radius, outer radius. If you remember this from like doing the area between two functions in Cartesian coordinates, or perhaps doing the disk method of surfaces of revolution, you had to do like pi r squared minus pi r squared. This is going to be 1/2 r squared d theta minus 1/2 r squared d theta. We're going to be integrating from 0 to 3 pi over 2. The outside, the bigger radius was, I think it was 2 plus sine. Is that correct? Yeah, 2 plus sine, and the inside was 1 plus cosine. So we get 2 plus sine here. 2. I just killed my pen. All right, I got to pause to fix my pen if it's possible. All right, I think I got it working again. Okay, so the outside was 2 plus sine theta. The inside one was 1 plus cosine theta. And now we just got to integrate, right? We just got to do the big integration. Again, let's just use a math engine to do it for us. Just got to put this great old big thing in there and then do the math. And I would do that in Wolfram Alpha, just like I did here. And I just have to change this thing to be the new integrand. I guess what I'm going to do is I'm going to pause the video once again and just put it in there instead of you watching me do it in real time. That way we'll save a little watch time for you. Okay, so I went to Wolfram Alpha and typed it in there, and it interpreted as 0 to 3 pi over 2 of 1/2 of the 2 plus sine theta squared and the 1/2 1 plus cosine theta squared. So I do think I typed it in correctly. It gave me this nice exact answer. You can plug this into a calculator to get a decimal approximation if you so choose. That's how you can do the area between two curves. Okay, and we get one last example here, which is over here to the left, which is, oops, can I do it? Can I do it? The length of one petal of r equals cosine 2 theta. So let's see what r equals cosine 2 theta looks like. Get rid of these guys. Boom, right there. So we're just looking for one of these petals, and we're going to have to find out the thetas. So what decides these? What determines where the petal starts and stops? Well, it looks like they start at a 0, an r equals 0, and go back all the way around to r equals 0. So I need to find out when this equation has r equals 0, and that will tell me a starting and stopping place, and we can try to find one petal that way. So I have my equation. I need r is equal to 0. So I get 0 is equal to cosine 2 theta, or I get the inverse cosine of 0. And I'm going to have to divide by 2 because that's equal to 2 theta. So theta is whatever this inverse cosine of 0 is. I need the x value to be 0. And where's the x value 0? Well, that happens at, it happens at pi over 2, and 3 pi over 2, or negative pi over 2, or negative 3 pi over 2, etc. Right? It happens lots of places. Is where we get the cosine equaling 0, or the x value equaling 0, the angle that gives an x value of 0. All right, so that's still messy. All right, let me try this again. We get pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. But remember, that's just the inverse cosine of 0. We still need to divide by 2. So it's this divided by 2, this divided by 2, this divided by 2, this divided by 2, right? So make sure you realize it's the inverse cosine of 0, which gives me a bunch of angles, divided by 2. Pi over 2 divided by 2 is pi over 4. 3 pi over 2 divided by 2 is 3 pi over 4. I get negative pi over 4. So I get a bunch of these to try out. This would be negative 3 pi over 4. Let me just try the first two, pi over 4 and 3 pi over 4. So go over here, do this as pi over 4 and 3 pi over 4. Hey, there we go. We get a loop down there. So there is one loop, so we can use pi over 4 to 3 pi over 4. I think also it works if you do like the negative pi over 4 to positive pi over 4. That gives a loop over here on the right-hand side. It doesn't matter. You just got to find one loop and do the limits for that. All right, what are we looking for in this problem? We are looking for the length of the curve. This is not the area of the curve. This is going to be the length along the curve, which if I can move this over, there we go. How do we find length? Well, that's one of our formulas that I talked about. It says right here. This one, boom, boom, right here. The length along the curve, integral between two theta values of r squared plus drd theta squared d theta. So let's go ahead and do that. Oops, let me zoom in a little bit here. A little more space. Length is equal to theta 1 to theta 2 of the square root of r squared plus drd theta squared d theta. Well, we know what r is. It's right there. R is equal to cosine 2 theta. But because we know what r is, we can find drd theta, just the derivative. Derivative of cosine is negative sine. Do got to use the chain rule. So I'm going to end up with a 2 in front, or a negative 2 in front. So that's supposed to say negative 2 sine, but it doesn't look so good anymore. So let me just make that look nicer. So negative 2 sine 2 theta is the derivative of cosine 2 theta. And then I could just plug it in. So let's see. Was it okay? I remember negative. I don't remember. I don't want to get it wrong. Okay. People are like, oh, Jim, come on. It was right there. Negative pi over 4 to pi over 4. I think I had another one before, but I'll just use negative pi over 4 to pi over 4 since it works. It's there. Negative pi over 4 to pi over 4 works. Square root of r squared, which is cosine 2 theta squared plus dr d theta. Dr d theta is, what is dr d theta? Oh, it's negative 2 sine 2 theta. So negative 2 sine 2 theta squared d theta. That, my friends, is going to be the integral that gives us the length of one petal of this curve. Plug it into a math engine to get an answer. And then we're done. We're done. I'm going to pause to plug it in so you don't have to see me fumbling with all my typing and getting it not quite right the first time. Okay, so I got it typed into Wolfram Alpha. This again is my integral, and this is what I typed in, and this is what it interpreted as. The cosine 2 theta being squared and the minus 2 sine 2 theta being squared, square rooted from negative pi over 4 to pi over 4. It gives me this lovely answer of pi times the square root of 5 minus 3 cosine 4 theta over 2 root 2, which we can get a decimal version of if we so choose. So anyway, so that's just the answer to what I'm really trying to talk about, which is how to do calculus using polar equations. So in this video, we did some polar equations. We found the area, radial area of a polar graph. We found the area between two polar graphs, and we found the distance along the curvy part of a polar graph. So hopefully this was helpful. And if you have any questions, please do let me know. And I hope you have an enjoyable day.